Okay, so now it brings us up to the Newton's second law for torque or for rotations, right? So we already see a little bit of that. Let's go back to our seesaw example, right? And have it at 5 and 10. And we realize if you put a 5-kilogram baby over here, this is a rectangular baby, but that will do. So you will have two forces over here, and we can calculate the net torque. So what will that do? Well, just like the net force, that will create an acceleration. But this time, net force creates linear acceleration. So net torque creates angular acceleration, and it comes with a moment of inertia. Okay, so let's see how we will fit that in, right? So this is sort of I'll keep this here. And remember, this is a vector, and this will also be a vector, okay? This is the moment of inertia. Just to be a little bit more precise, this is sometimes called the principal moment of inertia. Okay. All right. Yeah. So, but yeah, for most of the times, there is a more complicated version of moment of inertia, but we won't worry about that. Every time we talk about it, will be the principal moment of inertia anyway. Okay. So, yeah. So we can calculate net torque of this, and I think we've done. Let me just try and pull that up. Yeah, I can't find it. So let me redo it very quickly, so to give you a quick look at the practice again anyway. All right, so let's do it in full vector form in all its glory, right? So it's this torque plus this torque, all right? And then you want to choose a direction to be positive, whether you want the torque to go out as positive or inwards and positive. Let's have it go out as positive. So usually the reason is I can point my thumb outwards easier than I can point my thumb inwards, so I can sort of see basically rotating that way is positive. Okay, so also it follows the right-hand rule of what mathematicians like. Mathematicians like counterclockwise to be positive because you put your hand on the paper, that's sort of the direction it goes. Anyway, so outwards is positive k. Okay, so the torque 2 would be, so this is R2. Right, we will translate that so they originate from the same point. Force 2, same thing. R3, force 3, right? So you translate it to the same point over here. R3, okay? So this guy's gonna be in, so torque 2 is gonna be in the minus k direction. So this is the magnitude and the direction, okay? So remember how vectors work. You just write the magnitude and the direction like this. So it's that many units in the minus k direction, right? So yeah, so that's the minus k. It's the unit vector that points into the board, and yeah, you scale it by that much length, right? So here it's torque 3. Just to double check, this is in positive k. Yep, that makes sense, right? Okay, so now plug in the magnitude. We know that this is 90 degrees. So the sine included angle bit is going to be sine 90 degrees, and that's going to be 1. So we'll just skip that. So R2, F2. So this is minus k, right? And this is R3, F3, and positive k, right? So that will give me ultimately, let's pull out the k over there, and that will give me 10 times 20 will right. So that force is basically the weight of this. You can draw a separate free body diagram, but I think we understand that at this point, right? So you tie this. You just imagine this is located on here. So yeah, you're just tying on here slightly easier. Anyway, so yeah, so it's mg. The mass is that. G is 10, so 20, right? But minus plus 5 meters per and multiply by 30, right? Okay. Yeah, so we have minus 200 plus 150 k hat, so that's minus 50. Yeah, now it rings a bell. K hat. Okay, so this is what happens when you record videos separately. So yeah, so I just popped in the units there as well. All right, so here I got minus 50 k hat. Okay, so I'll suppress the units again over here because I want to find the acceleration, right? So just like before, we want to find the acceleration. Okay, so now we need to pop in the moment of inertia. All right, so we'll treat the Planck itself as massless. Okay, so this is very light compared to the two babies, let's say. All right, so so really we have a system of, this is the rotational axis, the axis of rotation, and I have a point mass of 2 kilograms at distance 10, right? So you can simplify the whole diagram in distance 5 and 3 kilograms, right? So what is the total moment of inertia of the system? Well, it's the inertia of this guy plus the moment of inertia of this guy, right? And what is the moment of inertia for point mass? Point mass is mass times distance squared, right? In this case, so be careful when you start repeating variables. We need to clarify this is mass 3 and R3, right? So we'll put the numbers in as well. So R2 is 10 square plus 3 and 5 square, right? So what's that? So that's 100. So that's 200 plus that's 25 times 3. That's 75. Is that right? 25 times 3. Yes. Yeah. So I got 275. What's the units for this? Well, kilograms meter square. Let's not worry about that. We want to worry about the alpha anyway. Okay. So this is going to go here, 275. That's basically the amount of inertia for rotation. And you have this. So this, what does that tell me? That tells me alpha is minus 50 over 275 in the minus k direction, right? So that's the magnitude. So let's just pop this into the calculator as well, and you can double check this with me. I think I got 0.182. Let's say if I just need two sig figs, I can just work with 0.18. All right, good. So what is the magnitude of this? So the magnitude is, right, so alpha is 0.182. What's the units? SI units, right? Radians per second, okay? Radians per second square, okay? Just like meters per second square. So this is the angular version of it. Change your meters to radians. And what's the direction? So the direction is obviously minus k hat. And just to translate it back to English words is out is positive, in will be negative, right? So it's into the board. So this is completely acceptable. This is acceptable. Well, this is acceptable only if you have written somewhere in your diagram like this, okay? And this is acceptable either way because this is, this is clear enough already. Or you can also say clockwise or counterclockwise acceleration. So into the board, right? So what is it? It's clockwise. So it's clockwise. So all these are acceptable, right? Magnitude and the direction like this, okay? And you now found the acceleration. If this does not ring too much of a bell to you, you can convert that back to degrees. You know what? Just to get a sense and also just some practice of doing that, you can do that. So how do I do it? Well, 1 radian, well, 2 pi radians is 360 degrees, right? So 1 radian is 360 over 2 pi or 180 degrees over pi, right? So radian is this, all right? Because this is identical, okay? So I can just replace this if you want. This is identical to 0.182. So write this as a fraction, and I have 180 degrees over pi degrees over seconds, right? So I've replaced radians with this factor over here. And now we can, again, pull out our calculator and go 0.182 and multiply 180, divide by around 3.14. Yeah, I was too lazy to put pi. I just put 3.4. But either way, you can double check if how close I have. But I've roughly 10.4 degrees per second squared. Whoops, almost. Yeah, so what does that mean? The angular acceleration, right? It's in the clockwise direction. So this guy is going to start to accelerate this way. And how fast? It's going to go from 10.4 degrees per second. So in 1 second, it's going to increase the angular rotation from 0. Let's say you put the babies there and it starts off at rest. Poor babies. So you put them there and start off at rest. So after 1 second, it will have the speed will be 10.4 degrees per second square. But after you get used to radians, try not to talk about radians and try to work. Sorry, once you get ready to get used to radians, try not to talk about degrees. Try to work with that, because now you can. If I ask you, well, so after 1 second, where will they be? So they will be. You can use all the Suvat equations. FAT square, right? Yeah, and calculate, but now promote that to the angular version. So how much angle will it have moved? So you will be able to say, hey, that goes away, plug in that. After 1 second, you can plug in that, and you can change, in fact, go ahead and try to calculate that, and you can see how much radians that will come out of after 1 second. So now you see the torque creates an angular acceleration, and then the rest is just angular Suvat and everything you've learned. As you can see, this topic of rotational motion isn't that complicated. It's a little bit, it's an extension, but it's basically sort of putting what we've learned sort of on steroids a little bit, right? I'll do one more example. That would be having rotating, let's say rotating a sphere, okay?